more chance for the contrast between the two different T2 tissue types, and there'll still be enough signal to work with. So I don't know if that was clear at all, clear as mud. So any questions about that one? So that was the fast. Okay, so let's get started on the topic for today. So the topic for this week is actually finally we've gotten up to the actual pulse sequences that we run 90% of the time on the scanner. And so this is a relevant week of lectures. These are the actual pulse sequences. We used that last one that I talked about, that T2 turbo spin echo, 3D turbo spin echo sometimes, but the ones I'm going to talk about this week are literally sort of take up 90% of the scanner. So they're generally called fast gradient echo, and just to put that into context, we should mention what slow gradient echo is, and slow gradient echo. So the most basic thing is we do a pulse, do a slice select, fix the slice select, do some phase encoding, and then go to the left side of K-space, and then go back across the right side of K-space, get an echo, and here's our original FID, and then wait a long time. So you could use this for a T2 weighted scan if you made your echo a little bit longer, but that's the basic slow spin echo, and just like slow gradient echo. So this will always be T2 star weighted, because this fall off curve here is the T2 star fall off, because there's no spin echo to correct the star part of the T2. So this is the GZ. I always write these wrong, but this time I wrote it right. And here's the RF sig. So the main idea of fast spin echo is go faster. So why can't you go faster here? Well, if you've done a 90, then it's going to take a long time to recover, and so that's one reason why you can't go faster. So you could solve that by just doing a smaller flip angle, and I mentioned this before. So if you start off with this much magnetization and do a 90, then you've got 0 longitudinal, and then it takes a long time to regrow. But if instead you just do like a 7-degree flip angle or a 10-degree flip angle, you've just barely touched your longitudinal. And so like the case of, remember we said if the flip was exactly 90, then you're in the steady state after the first flip, because the flip will always put you down to 0, and then you recover from 0. But we went through that exercise. If the flip wasn't exactly 90, there'd be some longitudinal left, and then you wouldn't be in the steady state after one flip, and it would take like 5 or 10 flips before you go to the steady state. The same thing is true in this case here. So that's the amount of transverse you get, and here's the amount of longitudinal that's left over. But that changes slightly, and it takes a little while. It takes a little while to sort of get into the steady state. So if you just look at a graph of the longitudinal magnetization, you start off here, and then you'll go down a little bit until you reach the steady state. So this is the steady state, and that's after this is flips. So it will take like 10 or 20 until you get to the steady state. So now there's two basic methods of doing this when you go really fast, and they can be classified as coherent or incoherent. And unfortunately, they have just a ridiculously various set of names. So the coherent ones are sometimes called grass. That means gradient echo something in the steady state. And they're sometimes called FISP. I have no idea what that means, actually. Sometimes they're called SSFP, which means steady state free precession, which contains nothing about, oh, sorry, man, I did this. Yeah, no, that's right, it's the coherent ones. Yeah, so steady state free precession. Then there's another one that is like PSIF, which is this one spelled backwards. I don't know what that one means. But those are all ones in which you, kind of like spin echo, you attempt to recover your existing transverse magnetization. So like in spin echo, what you do is you do a 90, and then you do a series of 180s, and when you're doing the 180s, what happens is you're recording data from K-space, but after you record a line of K-space, whatever line you went to, so if you for instance, start in the middle, and then you ended up, after doing some stuff, you're recording a line of data here, then you have to sort of like go back to the 0 point, sort of put everything back in order, so that you can record another line, and that other line might be, maybe down here. Who knows? It could be in a different place. But the idea is that since you've got leftover magnetization, you kind of repair it and put everything back, just very similar to like putting back the slice select pulse. So that's the coherent one. The incoherent one, probably the most neutral term for it would be fast low angle shot. So that's flash, but it's sometimes called SPGR, which means spoiled grass. We'll talk about what spoiling means. And there's a number of other names, but flash is or just sometimes it might just be called, fast gradient echo. So this one, or just spoiled. So what this one tries to do is pretty much get rid of the magnetization as best as possible, so that you can record another line of K-space. It can't really get rid of it, but what it does, it can make it incoherent so that it all sort of cancels out. So, and that's one of the most common ones. That would be very similar to the MP Rage. That is one of the most commonly used structural T1 weighted scans. So let's start off with the coherent ones. So the GRASS, FISP, SSFP, PSIF, True FISP. There's a whole bunch of different ones. So this one starts off with an RF pulse. It's typically not a really a really high flip angle pulse, because we're trying to sort of not lose our transverse magnetization or longitudinal magnetization. And now the first difference is that since this one is a coherent one, we have to, so we're doing a slice select or a slab select, but we have to sort of prefix it. And why do we do that? Because there might have been some magnetization around. And so you can sort of divide this down the middle. So if we conventionally assume that the RF pulse starts right at the middle, then this area over here has to be the same as this area. But then we've got the first half before the RF pulse started. And so that one's going to mess up any pre-existing magnetization, mess up the phase of it. And so what we do is we prefix it, and then this one sort of like cancels out this. Then the RF pulse conventionally starts. Then we mess it up because we have to do slice select, and then we fix it up again. So that's that would be the slice select direction. And you could do this as a 3D sequence. So if you did it as a 3D sequence, then you might have some phase encode steps here. And then here's the regular phase encode. So this would be the partition direction, and then this guy is the regular phase encode direction. What those symbols mean is you have to use all the different combinations of those two phase encodes. And then we have the readout. And so with the readout, again, we've got to sort of fix the end of the readout, because we get the echo sort of halfway through. So here's where the echo comes, but then the later parts of the echo are being damaged by the readout gradient. And so so after we finish the readout, then we have to, so this has, this area and that area have to be the same. So we kind of, fix things afterwards, and then we've got to fix all our phase encodes afterwards. So if we did some partition phase encodes, we have to fix those. So those, if we went up on this side, then we have to go down on that side. And then we're ready to do another one. And so now we would have another prefixer and another, slice. So here's the next RF pulse. So basically here's the end of the first one, the first unit. And so with this you can go very fast. So the time here, can be like 7 milliseconds. So very short. And so that's the TR. And then this guy is the TE, and so that could be like, say, 3 milliseconds. So it's possible, very similar to the case of the ultra-fast spin echo, then you can record the data quite quickly. This is RF signal. So So what do these images look like? You might not have heard of these before. They have quite a strange contrast. So what the contrast, then let's put, so partition, so this was second phase encode, which is, the partition direction, and this is phase encode, and this is a readout. So if you look at the equation for the signal amplitude, it's kind of complicated. I'll just write it out, but we'll sort of simplify it down. So there's some constant, there's the sine of the flip angle multiplied by a huge mass, which is 1 over 1 plus the cosine of the flip angle plus 1 minus the cosine of the flip angle times T1 over T2. And then it's also decayed a little bit. So e to the minus T over T2. So it's kind of a big mess. But whenever you have something like this, we always have to sort of make it a lot simpler. And so what is our simple version? T2 over T1. So, or T2 star over T1, because we're not doing spin echo. So how do you get that out of that? Well, it's T1 over T2, but it's 1 over T1 over T2, which is basically T2 over T1. So it's T2 star over T1 weighted. So if you take various tissues and look at what that is, for the brain, it's about 0.1 for, what do I have there, fat. For fat, it's 0.3. For cerebrospinal fluid, like for fluid, it's 0.7. So it's got just an enormous contrast. So if you look at one of these scans, they have extremely bright CSF. Is just have like white anywhere where there's fluid, it's bright white, and then it's the brain itself is quite dark. So what have people used these for? One of the things that they were designed originally for like heart imaging, because there's a lot of fluid in the heart, and so you can really visualize that fluid quite well, and you can, if you do a 2D sequence, you can do these very quickly. When I was in London, I did some imaging of the tongue with this. So if you just take one slice and then turn all the things down as short as possible, you can easily get up to about 10 images per second. And if you fiddle, you can get up more like 20 or 30 images per second. And so you can actually, that's fast enough that you can actually visualize the movements of the tongue in the scanner. So we had people like pronouncing different consonants, and you can actually sort of see the tongue moving in the scanner. I remember we got a presenter from the BBC, and she went in the magnet, and we tested this outside the magnet to make sure she wouldn't drown in the magnet, and she first lay on her back and swallowed like a banana milkshake, and that was an amazing movie of, you can see the banana milkshake sort of, you can see the flat top surface of the banana milkshake, and then during the swallowing, you can see the trachea is open, and you can see this sudden closing of the trachea as all the banana milkshake sort of goes goes down the right pipe. So yeah, so you can use it for all different kinds of things. There's even been an attempt to use this kind of sequence for functional MRI. So if you want to look up, there's a sequence called BOSS. I can't remember what that stands for, but it's steady state. And so you can use this for to try to use it for functional MRI. It's a little touchy. One of the problems whenever you have a sequence like this, where you're trying to save all the magnetization, little imperfections can sort of build up because you're kind of saving all this magnetization, trying to fix it. But if you slightly misfix it down the line, you start to get various kinds of artifacts. And so it hasn't really sort of taken off as a method of doing functional MRI, but because it has some T2 star weighting in it, and so it should be able to help with bold. But that's a strange sequence. You probably haven't heard of this one, grass. You've probably heard of this one, SPGR, spoiled grass. But this is grass. This was actually developed quite early on because you can see it's sort of analogous to spin echo, turbo spin echo, where you keep you fix everything up after you're done, and it sort of seems like it's unwasteful. You've got all this magnetization. Why not just save it? But it turns out it's actually quite rarely used. So what is the one that's most commonly used? That was the coherent one. This is the incoherent one. And so for the incoherent one, pretty much there's not much to it that's very different. We just do our RF pulse. We're in the steady state. We're assuming that you were in the steady state. And then we maybe do a slice select. And so this goes here. Then we do some, if it's a 3D sequence, we do some phase encoding on the partition, and then phase encoding on the phase encode, and then go to the left side of K-space, do a readout. So that's all the same. And there's a gradient echo here. And that gradient echo is T2 star weighted. But now, again, we're talking, a very short time, so like 3 milliseconds. And the time to the next pulse is, again, very short, maybe 7 milliseconds, something like that for the TR. So this is the TR, 7 milliseconds. This is the TE. And so now we're ready to go again. But the problem is we've got a lot of leftover magnetization. And so that's why we spoil it. And so how do we spoil it? So one way of spoiling it is we could just put on a random gradient, a large random gradient. And so random amplitude. And so the idea is what we want to do is just, if there's some transverse magnetization there, just mess it up. But if we mess it up in exactly the same way, then what will happen is it will come back and bite us. And so what we do is we just sort of just pick a random gradient and just sort of sometimes wrap it up to 240 stripes, sometimes wrap it up to 370 stripes, just sort of randomly spoil it. So that's called a spoiler. A spoiler, because we're spoiling. Spoiler. Because we're kind of spoiling, as opposed to a crusher. Like a crusher pulse, the idea is you're trying to completely destroy the magnetization. Here we're just trying to spoil it, not completely kill it, just kind of mess it up in a way that it will be incoherent, so it won't appear later in the sequence. And there's another way that you can spoil. So this is called a spoiler gradient. But you can also do RF spoiling. So RF spoiling. So when we do the next RF pulse, so whatever the phase of this guy was, we set the phase of the next one to whatever so here's the previous phase. So what's the previous phase? Like, where did that come from? So normally, if we do an RF pulse, and we normally do it with 0 phase if nothing has happened before. So that just means we'll start, say, pointing along the y-axis, so that when the transmitter is turned off, it effectively sort of starts time t equals 0 at a 0 phase angle. But what we could do here is we can set the next phase to, it turned out, I can't remember what 117. So doing simulations, people figured out that if you offset each successive pulse by 117 degrees, it optimally messes up the magnetization from the previous. So this is RF spoiling, so each time so that you can imagine the protons are precessing around, and if they're going like this and you hit them exactly at 0 phase, again, that's going to make the signal bigger. But if instead you kind of wait until they've went around like 117 degrees and then you hit them with this phase, that turns out to be the optimal angle to make them incoherent and kind of mess it up. So both of those things are done. And then what that allows you to do is effectively, go forward as if you had no previous RF pulse. And so here's the, the rest of the, here's the next readout. So this is a very common pulse sequence. So when you start the scanner, you do a localizer. It's one of these. It's a quick sort of a quick scan, and since the TR is so short, you can cover lots of lines. So if you hear one of these scans running, it just sort of sounds like it's just like a continuous pitch, and that continuous pitch comes from the fact that these gradients are happening every 7 milliseconds. So it kind of like makes it makes a 7 millisecond sine wave sound, roughly. So that's about 100 hertz. So this is like 130 hertz. So it's 100. So you're doing 130 readouts per second. So it just makes a continuous noise. So you can't hear any sort of variation in it. It's just a continuous noise. You can hear a slight variation as you go to different parts of, as the gradients slightly change. So it often has a feeling, this kind of crescendo feeling, like you can hear as the gradients get stronger and stronger, you can actually hear that or feel that. So that's the sort of the standard. That would be like an SPGR or a flash. But it's still, there's a good 25 minutes to say what we actually do. So that one is, you can get pretty good T1 contrast with this. And if you look at, we went over, this is the one that we went over the actual equations for. So, that was in the homework. So if you plot that graph, you get something like that for one tissue type, and then another tissue type might be something like this. And if you subtract the two, you get, you'll get something that they go through 0 here. So So it goes up and then it goes down, something like that. So that would be the diff. So it's possible, and this would be like about 10 degrees here or something like that. So you can get, either gray matter brighter than white matter, or vice versa, depending on what you set the flip angle to. This was the flip angle. Now, when we drew out this graph, it wasn't for the coherent one. So this is incoherent only. Incoherent, spoiled. So you don't get this. This thing is different. So this, I didn't go through the derivation of this equation, but it's different than the standard steady state incoherent equation. So why aren't people satisfied with that? Well, it turns out that that you can get quite a bit better gray-white matter contrast by doing something that's it's not even a steady state scan. So one of the most common ones is this scan called an MP rage. And that means this one is, the MP is means magnetization prepared. But really what this means is something that is like an inversion recovery. So it's kind of somehow putting an inversion recovery into this. But you'll immediately see what the problem is. If there's an inversion recovery, that's not a steady state. So this is not steady state. So all of these are kind of gradient recalled something in the steady state. So all these assume that you've reached this steady state of magnetization. In this case, you'll start off, you'll start off, and then each additional flip will eventually reach a steady state. So here's the steady state. That's longitudinal. So this is radically not steady state. And so what does the sequence look like? So sequence looks like we start with a 180. So this was a little bit bigger to draw out. So we start with a 180. And this potentially could be it could be a slab selective one if we're so in which case we'd have to do the funny ears. So here's the little crushers. So that's selects our slab. You might want to do a slab selective if you were doing something like, if you're doing an MP rage that say stopped at the chin and you didn't want the body to get excited. So then we wait a while, and so if you listen to an MP rage, you'll hear sort of like you'll hear a tick, and then a little bit of a space, like a half a second space, and then you'll hear and then there'll be a little space, and so you can hear this repeated spaces. So what's happening is we started off with our longitudinal magnetization, which was almost recovered, and then we did a 180, and so the 180 is going to go all the way down to sort of negative equilibrium magnetization approximately. And then we wait a while, but then we start doing something that's like a flash. So we paste a flash onto this one, and so what does that look like? So that looks like we do a small echo. So here's an alpha pulse, a small flip angle. So instead of 180, this would be, for example, 11 degrees. So a much smaller flip angle, and so that one we could often just do that one as a little hard pulse. So don't even bother. We're trying to sort of like save time, so don't even bother doing a slice select, just a hard pulse. We did a slab select on the inversion pulse. So that would commonly be done. And then it's a 3D sequence. And so we would have our phase encode here. And here's the partition phase encode. And then here's the readout. And then maybe might do a spoiler and some phase spoiling. But basically what we have to consider now is we're not in the steady state. So what's going to happen is this should give us no signal. If it was a perfect 180, there's usually a little signal, and we try to crush it, but basically no signal. And then what's going to happen is this guy will give a signal, and then we'll get an echo here. But those echoes are going to be happening at all different parts of the recovery curve. So if we actually look at the longitudinal magnetization, so here's something about MZ0, and then we do a 180. So here's the 180. So now we're sort of at negative MZ0, and then we start recovering, according to the Bloch equation, and there's a little gap in time. So compare that with the steady state. The steady state, we would have done a whole bunch of RF pulses, and we would have reached a steady state that was almost as big as MZ0. But this is radically not steady state. So we go down to negative MZ0, and then we start doing all these alpha pulses, maybe 100 of them. And so there's a little alpha pulse. We sort of flip a little bit, and so then there's recovery. So there's like a whole series of jagged alpha pulses like that as it crosses 0. And the goal is, we're hoping that there's like another tissue type like this, and it's doing all its little alpha pulses. And so we're hoping that tissue type, when you cross 0, is going to be considerably bigger than the other tissue type, and so you get a bigger signal out of it. But only for that one point. So here's all those additional alpha pulses. So what is that one point? So that one point is arranged to collect the center of K-space here. So there's basically, the regular inversion recovery that we talked about at the very beginning was, you go down, and then you wait, don't do anything, and then you wait for recovery, and then you've got another guy that's recovering, say more slowly, like that, and then right at that point you just do one RF. And this one has a big signal, this other one has a 0 signal because it's going through 0. So this is like, this is like a strange thing. You basically just arrange to collect the center of K-space with a high contrast between gray and white matter. So this will be essentially only one point in K-space that has this this high contrast, and these other points in K-space are going to be recorded with differing amounts of gray-white contrast, different spatial frequencies. So remember, each one of these things is one line of K-space. So all these different spatial frequencies will have different amounts of gray-white contrast. But when you actually look at the final image, it looks pretty good, and it looks a lot more contrasty than a standard flash scan. So that's the strange, strange MP range. So it's a non-steady state scan. Now, one of the problems with this is that there's various conventions for the inversion time. So the standard, if we just did one RF pulse, the standard inversion time, this would be the inversion time, TI. And then, there'd be a small echo time. The echo time is, here's TE. It's going to be much smaller. And then, maybe we wait a little while, and then finally we do another one. So, we wait until we recover, and then, eventually, say at this point, then we do another one. And so so here's, there's the echo time, and then this guy would be the full, repetition time before we do it again. So what are we going to do over here? Here we've got, the repetition time is the repetition time, between these guys. That's what I would call the repetition time, because that's kind of what controls a lot of the contrast. But on the Siemens scanner, they decided to call the time to the next 180 the repetition time. So, so not making it like the fast gradient echo. So I would call that the repetition time, and then I would call this guy over here, that is the echo time. So the echo time, would be like, equals 3 milliseconds. This guy would be TR equals 7 milliseconds. And then the time to the next 180, so then there's a whole bunch of, a whole bunch of like 100 readouts here. So that, the time to the next 180 is going to be like 2 seconds or something like that. So here's the next 180. So that's in Siemens, that one is called the TR. And then Siemens calls the thing that would normally be called the TR, they call it, let me just move this. Yeah, I managed to do it wrong. So let's put the gap here so I can put in another readout. So then we would have another phasing code here, and another readout here, another phasing code here. Better. Okay, so they would call, and so there would be another echo over here. There's a little FID we didn't record, and then an echo. So Siemens calls the TR echo spacing. So if you look on the scanner interface, this is called echo spacing, which is, you can see the echo spacing is the same as this time here. this time here, which is the TR in between alpha pulses. So it's a little, so you'll have something like the TR will be listed as 2.3 seconds, which doesn't make sense for like a fast gradient echo because it should be like about 7 milliseconds. But it's just because it's kind of it's a weird combination of like inversion recovery essentially just for the center of K-space, but then record all this additional data. So what I didn't write out here is, so then we stop recording at some point and just continue to recover. Continue to recover. So both of those guys are recovering. Then we do another 180. So there's another 180 here. And then we wait a little while and then start recording again. So you can see there's a lot of different things that you could call, inversion time. So typically so you could call, on some scanners you might call this the inversion time, this time here before you start recording, but that's not really the inversion time. Like this is the time to when you record. The center of K-space is kind of the effective TI, because that's the one that really controls the contrast. I think this one sometimes is called TD for time delay. And then the time when you get to the center of K-space from the 180 makes sense as the actual inversion time. And then the time between the 180s could either be called the TR, or in my mind more sensibly you would call it, the TR between the alpha pulses. So that's the most common T1 weighted scan. And the reason people use it is even though it's got a slightly strange non-steady state thing, is because the contrast is much better. So you can get twice the contrast from an MP rage compared to sort of an incoherent, spoiled grass type scan. Okay, so that's one of the most common T1 weighted scans that's used on a regular basis. So we finally got to, again, it's a slightly twisted thing, because you've got this non-steady state thing going on, but it has extremely good gray-white contrast, and so people routinely use it. Okay, David, we'll end the recording there, and I'll get ready to take some questions.